Man, she did not do me right. Put that over there.
You know, I was playing with it this morning before class, and I had it where it was at, and it was working pretty well.
Hey, put the stream on. See if it's up. The lighting is kind of terrible too, man.
Yeah, dang.
Sorry. Is up? Is it up, Don Ray?
Matthew, I'm on the wrong account. Williamson.
It's up. I've got notification.
Okay. It's literally your name with "on" at the end of it.
It's frozen, sir.
Can you? Yeah, it's the computers have said that you don't know how to spell your last name with 2 letters at the end of it.
Where you at?
God.
Is that you?
I'm probably not gonna put this on canvas. Can you hear? Like, can you can hear it?
You just hear off my phone?
Hello? This is what it looks like when you're reaching them keys. Very beige. Yeah, it's good. Okay. Well, we'll start it up. So today we're going to be going over the introduction to OpenGL. So this is a fluff lecture. Yeah. It's going to give you some overview about some of the things that we're going to be covering. Okay? So what I'll ask is that everybody like get away. If you is anyone typing notes? Sweet. So just kind of get away from your desk and like make sure that you're at least you're normal. You're facing me. Okay. So just pay attention, take notes on your lap or whatever, and then we'll go about it. You do it in Sweden, and they are really smart. So this is totally not going on canvas. So. What is graphics? Everything. Anyone else?
What you see?
Graphics, what you see? Wally? It's almost like you were on the inside. Anyone else? Graphics, what are graphics? What's a graph?
Different formations of pixels arranged.
It's on the screen.
Formations of pixels in different colors.
Okay, so bro version then, like what are graphics in terms of video games? When I'm buying a video game, what about the graphics is important?
How clear that shit looks.
Man, it's on the internet. It's over there. So, graphics, good graphics. What are good graphics? But the point of that was like you go play a game and you're gonna want some graphics. Like up until this point, you've had like console application. Is that graphics? Opposite of that, is it graphics? Is something that you can see some visual representation, okay? But when in the terms of what we're going to be talking about, graphics definition is going to be very clear what we're talking about. So when I gave this presentation in school, I started it off with this, and I did it because I knew this guy. It was a setup. I knew he would say something. So what is a shader? Yes.
A shader is how the light hits the model and places
No.
Goodness.
So yeah, and that's how I hit him with it. I just told him no because what's up?
A post-processing program?
No. It's a type of shader. So shaders it's an abused term because you can have a shader that only does computation. It only just like solves a problem. Okay, it just does computation. So, is anyone familiar with folding at home? Folding at home. Okay, it's in reference to. Yeah, no, I don't. No, unless they're towels. No, folding at home is a. I want to say it's a company, but it's like an organization that uses the extra processing power to solve problems. It's called code folding. Okay, so what they do is They do a bunch of computations on your graphics card whenever you're away from it, okay? And then they kind of rate people, all right? So the programs that run on the graphics card could be considered to be computational shaders, all right? So while there is OpenGL, there's also other libraries developed by, I want to say Kronos does the one I'm about to talk about, but OpenAL, Open Algorithmic Language, maybe that's what it stands for. Yeah, so shaders, it's just an abuse term is the point that I'm trying to make, okay? So we'll move on to the next slide.
So what is a shader, an abuse term?
So shaders are a program. That's why I just kind of looked away whenever he said it, because it's a program, and it's as soon as you start to drill down, you start to talk about the different types of shaders. The assumption is that like you have something the way that it is, but then you want to manipulate and change it, so you just kind of color it in. You know what I'm saying? It's like you have data, but then you want to manipulate the data without being volatile about it. All right, that's a good way to remember like how shaders work, because what we do is we buffer all of our data up, our positional information, then use shaders to not mess with what the original setup of it is. Even though things are moving, it's the shader that's actually doing the majority of the work. When you guys load up Unity and you have all that good running, and it looks really cool, that's millions of that's programs running and happening, okay? Connor, you got that? Okay. So, the overview and goals of this presentation, we're going to talk about a CPU versus a GPU. We'll talk about why you would use a GPU. We kind of already talked about it. We'll talk about the graphics pipeline. We'll talk about some shaders. We'll also talk about physics simulation. Why would that make it in there? Seems like math that you could solve. Yeah, totally. So those lines are actually because of the driver on the graphics card, by the way. That's not what I was going for, but those arrows, yeah. We'll talk about help with getting more involved in graphics programming. Once again, this was a 2013 presentation that I did, so it's actually the process to get involved with it is a lot easier, okay? And then provide an abstract overview of graphics processing. Okay, so that's the overview and the goals of this presentation. I'll put that disclaimer because guess what? If you go to if you go to a school and you got like 30 people graduating class and you're the only one playing D&D, guess what? You got nobody to play with, so you're not gonna have a good time. This was me in college. I had no one to do graphics programming with. So in my presentation, it was like, hey guys, you want to do karate and maybe a little bit of graphics? Okay. That's why I put that up there, to make it not as hard to get involved with it, because the setup is rigorous. Okay, here we go with the memes. That multiprocessing though. So, what we have here is a description of single instruction. I don't know what, damn it. I should have.
Direction?
No. I'm not gonna Google it in your face stream, I promise. But anyways, on the left we have single processing, and then on the right we have multi-processing. Okay, this is important because what do you need to process? Okay, it's like you process. So you have a problem in front of you. Like if you're walking down the hall and it's you have a wall, unexpected. What do? You move. There's some process that runs. You need to solve that problem. Okay, so you just go the other way. So you only have one brain. All right, that was supposed to be some type of analogy with respect to this. However, if you have multiple brains, you would be that much more better. Maybe we'll talk about it. Okay, so what is involved in multiprocessing, and why it is relevant. Okay, so this is how instructions are fetched, decoded, and executed with respect to multiprocessing. Okay, graphics cards have thousands of processors on them, CUDA cores. Yes, and the specifications on Newegg, if that number's big, it's good. All right. I'm just gonna walk over. Or take the mouse with me. There we go. Okay. Did you Google it? What does it stand for? Single instruction.
Single data.
Okay, single instruction, single data. Single instruction, multiple data. Okay. So, multiprocessing. My computer doesn't have enough cores to properly test my multiprocessing code. Depression.
Yeah.
Yeah, man, if you're writing a program for a toaster, you don't have a toaster, it's aggravating. Just like if you were to be writing programs or video games for the Oculus, and then guess what? You didn't have an Oculus. I guess you're just playing Army at that point, playing pretend, okay? So, the introduction of multiprocessing and CPU architecture helped pave the way for GPU architecture, all right? And I'll explain that here in a second. GPUs sacrifice latency for throughput. So more is better. And it is the future of computing. So start learning it. That was me. That one's just me.
You just telling your whole class?
So, huh?
You just telling your whole class that?
What?
You said you did it for 13?
Yeah. When in school?
Yeah.
So I just, what do you mean?
Did you put?
You told them that this is the future, so start computing, so start learning.
like in
Yeah.
front of your class?
Yeah.
You would say.
What?
You would say.
Yeah, oh yeah. So, smell like cabbage. So yeah, it's the future of computing, so you should start learning it. Analogy time. Latency versus throughput. Okay? So, CPU, fast like Ricky Bobby. Okay? A CPU, when it needs to do an execution, will go very fast and go do it. It'll do it immediately, right? This is just like, this is definitely going up on canvas. It's like a crackhead, all right? If you told a crackhead to go to the store and get you some, he's out the door for you, like he's gonna get your money first, okay? But he'll go get it, and then he'll run. He'll go, all right? He will get tired, all right? So that's how you would look at maybe like a CPU. So a GPU is different. GPU says, what if I just bring the store to me, okay, and then put multiple stores around me, and I'm just gonna sit and grab and grab. That's why the GPU is super relevant, because the data is on the card. It's buffered onto the card, okay, Zyron? It's buffered onto the card. So then, since it's already on the card, that big data, your textures, all of your vertex information, it could do complex arithmetic operations on them because it's just there. Before, you had to have a CPU translate and then do it and go through the entire pipeline while you were in your program, okay? If I take my shirt off, just, you glazing. Oh, we don't. All right. So, that's basically the gist of this, okay? The next one. So, more is better. Notice that the GPU is actually bigger in the picture, therefore it must be better. No. So, GPU cache is read-only, therefore there is no cache coherency. We'll talk about that here in a second. GPU cache is very small. It uses first in, first out. CPU uses round robin, so it tries to keep everything in the cache. All right. So, this right here is basically just a demonstration without having to go into those algorithms, okay? What's up?
What does round robin mean?
It's like it'll pull in cycle. Like it pulls them. Not pull, but pulls them, okay?
Yeah.
So these are actual algorithms that you can look at in regards to cache, the way that instructions are stored and fetched. Like your processor actually has a cache. Whenever you funnel operations to it, it just saves what the last instruction was. Okay, but then it pulls it off because it's not the last instruction, and it just like keeps discarding them and moving them down the road. Like it just keeps going. Okay, because I mean, if you needed to know what the last operation was that occurred, that would be a nightmare if you didn't just keep track of the last operation. Okay, so the GPU's cache.
Wait, so does it have? Is the cache before or after the process?
What you mean?
Like.
No, that's just okay. It depends on the how it's implemented. Okay, that's just a general idea of like cache coherency with respect to the instructions that funnel through. All right, the cache and then the buffer are going to be two different things that we talk about. This is not it. So that was a setup. Yeah, CPU. The claim was that the GPU was better than CPU because it was bigger, and then some other very generic terms, general ideas. So. It's not really better, okay? They're two different. They have purposes. You know, do you use a Phillips or a flathead? Depends on what kind of screw you got, man. Come on. Where one of them could actually be used for the other one, all right? So, even though GPUs are great at some things, they are still proprietary in nature. So they're designed for a very specific use. What is that specific use? Graphics. To process graphics. Okay? You can use them to do computation. Whenever I worked at Light, we had an entire data center dedicated to doing computation. All right? There were no graphics involved. It was just doing computing. So, GPU likes big data to process in parallel, like your texture information, like your model information, okay, like animation, like FBX information about keyframes over time. And CPU likes to go fast. It's like Ricky Bobby, okay? So, he's Ricky Bobby, and then if you don't like CPU, then you must like GPU. If anyone gets that. No? Has anyone ever seen that movie?
Yeah.
I
I don't know what to do with my hands.
Do you know what he says after? He says, if you don't like big red gum, okay. Beep. Yeah, he does a beep. So the GPU specific use, it's made to process graphics. Once again, big data in parallel. Graphics are awesome. What is a graphics? They're awesome. Look, I just said what it was. You can see what it said.
They are. not what it
Okay.
is.
They are awesome. Look above. Okay, what is a graphics? What is a graphics? They are awesome. I think it was meant to be worded the way that it was. All right, so let's look at what graphics are. This is graphics. Sweet. It's a bunch of dots, right? Well, math is for much as like processing. So how do we get this up? So what are you guys seeing?
Connect the dots.
You must have a problem with your mother, right? It's like the ink blot, miss. He's obviously got problems with mother. All right, so I'm gonna need that. I'm gonna need that. I'm gonna need that. I'm gonna need that. Hey, you. No, why would you do that? All right, so this is the graphics pipeline simplified, and you see your boy. Yeah, pipeline though is looking like it has colors that are in between one another to denote some type of definition here. Okay, so this was definitely the slide, right? Yeah. So this is the graphics pipeline. Test question. This is on the test. All right. So what are the different stages? So we'll look at it. We're going to talk about the vertex generation step. Then we're going to talk about processing it. All right. We're going to talk about the primitive generation step. Then we're going to talk about processing it. Okay. After that, we're going to talk about the fragment generation step and then its process. And then we will talk about the pixel operations and how it goes to the screen. All right.
That's not something you change, right? I was writing it down, coach.
I'm going through every one of them, bro. I'm going through every one of them. So the first step, well, you almost done writing it? Just go ahead. VGVP. So if you put vertex, primitive, fragment, and then pixel, it's processing, it's generation, then processing, generation, then processing. Okay. I don't know why this is still here. Like, why would it? Does this gear do something for me? It does not. No. All right, so let's talk about vertex generation and what fixed function means. Fixed function is important to note. Fixed function. The fixed function OpenGL pipeline is different than the shader pipeline, okay? Fixed function means no touch. You can't touch it. There's no touchy right here, okay? You have programmable layers in this pipeline, which mean that you can write code for it, but then you have layers that you cannot. So, the vertex generation step. fixed function layer where the raw geometric information is received from memory and then turned into vertices. So you're going to be giving your verts to the program, right? So your verts could look, if we had it up on the board, like what we had over there, you would have your verts defined to be like this. So V0, V1, and then V2. They also have pictures here. But these are your verts, okay? So your verts contain positional information as well as color information, UV information. They could contain a lot, okay? It depends on what type of problem we're trying to solve to see exactly what we want to put in a vert. The disclaimer is that just because it's a vertex does not mean it is just position. That's what I'm trying to get out at you, okay? Vertex could contain like bank account information, okay? Like, just, I mean, it's literally just data. So, the information received is called vertex descriptors. So, points, lines, and triangles. We then make a stream of vertex records to process subsequently. Nope, not yet. Not yet. We have to have the stream of data, just like your STD streams, okay? With your the characters that go out. We have a stream of data that we're going to manipulate, but we have to tell it how the data is going to be given. So these are points, this is color, and so on and so forth. And then the shader is going to be written in a fashion that will support that. All right? So vertex processing. This is what we can write code for. So vertex.vert. All right? This is where we are going to actually process the verts that we're given. Vertices are transformed into screen space independently. It doesn't care, all right? Vertex records are computed into a perspective image. So we're gonna go over what that means. But your vertex shader will always output positional information, or it will return positional information, okay?
Vertex shader?
Yes. And it feeds to it feeds to the geometry shader, then that goes to the tessellation shader, then that goes to the fragment shader. Okay, and we'll see it here in a second. So primitive generation. So now that we have just dots after we've written our shader processes, and let's say that we did not touch anything, we just said whatever your position is for those verts, I'm just going to transform them into the screen space. I'm trying to be general because we're going to go over that later here. So you have to basically take those positions and then put them somewhere relative to the screen or your window that your program. Okay. Any questions so far? I know I'm kind of breezing over it. Any questions? Okay. So we have to generate some primitives. So this is a fixed function layer that takes the vertices from the previous stage and groups them into an ordered stream of primitives. All right. What's a primitive? Well, I mean, yeah, okay, what? So in this definition, a primitive is going to be the triangle that gets generated. And you're about to see it, okay? We're going to have one triangle per. All right? When we give verts out, we're going to... Here, I'll show you. All right. So primitive processing. So programmable layer where the shape is created. Operations are performed on each primitive independently. You see why the GPU is such a beast now? Yeah, your geometry it's going to manipulate everything independently, all right? So, everything on this slide will be on the test. Like, you can basically bank on this, a lot of this material just being on the exam. Zara. So, operations are performed on each primitive independently. Like I said, that's why the GPU is such a beast. It will produce an ordered stream of output primitives. Okay, so you're going to generate the shapes. Then what do we do with those shapes? Which one is in front of what?
Yellow's in front of the blue.
Why?
I see the lines open. It's the last thing I got put.
3, 4, 5.
That's a good assumption. That is a good assumption to make, and you'll see why. What's going to happen here? Notice how they're on a grid.
Is this one object? Is that
So
one
now we're
object?
going to talk. It's two. No, so you're going to see. Yeah. So fragment generation. You cannot touch this. Okay, this is fixed function. So a question on the test would be list all of the fixed function layers in the graphics pipeline. List all of the programmable layers in the shader pipeline. Say again? No. No, so you could just take the notes. So, fragment generation for fixed function. So, rosterization is a procedure that samples each primitive record on a bounding box that we define, also referred to as screen space. So, this is how I explain it. You take a piece of paper and you have a George Foreman grill. Alright? You put the piece of paper on the George Foreman grill and then you slam it down. What do you get? Assuming that this George Foreman grill is like has a bunch of squares in it.
Okay.
And then you slam it down. What do you get? You're gonna get a grid. Then I'm gonna take some metal and put it in the George Foreman grill on the paper. And then slam it. What do you get? What? Yeah, you're gonna get like the lines over the squares is the point that I'm trying to make. It's basically rasterization step is like pancake mixer, okay? So you're taking your geometry and you're figuring out what lines intersect or go through each pixel, okay? Then we're going to take the squares that make up each one and then do something with it, okay? If you need to stand up, just stand up. So takes each sample and then creates a fragment record. These fragments are given to the next stage as a stream of records that contain the output image position of the sample as well as some other information. Each fragment is processed in parallel. Important, man. Important because it's in all caps, but it's to hammer away the fact that like your GPU is doing parallel processing and it's killing it.
So you're saying it's doing all that at the same time if I have 100 objects?
It's doing them in parallel, one like boom, 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 boom. Like you have all of this stuff happening at one time. Rap, rap, rap. So yeah, it's pretty amazing. So many algorithms, and I don't know how to do it, but now I do actually. So this was back then. So the rasterization step is this was before I took computer graphics. The raster step is how you generate the squares. You can do like point slope theorem, okay? It's called scan conversion, all right, is the algorithm. And you have midpoint algorithm. There's a bunch of different algorithms that you could have, but basically whenever a line goes through another square, so you define this grid or a pixel buffer, okay? And then you have the coordinate information for each individual pixel, and you know where the lines start and end at. You could calculate which ones are going to be within that it's going to intersect, okay?
Yeah.
Make sense? All right, this is just an idea of how that works. So this is what you would get separately. So those are the fragments. Okay, so fragment processing. This is in the programmable layer, and this is where the really good comes in. This is where we do the lighting at. Okay. This will take the fragment records that we get from the previous stage and colors the fragments accordingly. So different shades of fragments because one of our triangles overlapped the other triangle. This is where the culling comes in. The culling. So like if one lays on top of the other, right? And you already drew this one, and it took up pixels that were part of the other fragment, and which one's going to get the color? Yeah, the one that's defined to be in front, and in front means the z, like whichever one has the lower z value, depending on if you're doing positive z this way or this way. Okay, so does that make sense? Okay.
Like camera culling is done there?
Yeah, so that's where you would do something like just culling in general. The idea of culling means that you're like getting rid of something. You're cutting it out. Okay. We're not talking about camera culling yet. This is basically just the culling of like an object behind another object. Okay. Does the object behind it exist? So on and so forth. Like yeah. So whenever you have to get it up on the screen, know that it's in 2D. So you can only have so much contribution in one area, and one is going to take precedence over the other one unless it has some property about it that's called its invisibleness, also known as its alpha. Throw another number in there, dog, and we'll call it the invisibleness. And guess what? If their invisibleness is like half, what do you think is going to happen to that color of that fragment? Well, it's going to take on a mix of both colors, right? Because colors are additive. Okay?
Is it something we implement?
No, no. Oh, and note the tone. No.
Okay.
Alpha implementation is non-trivial.
No, I'm talking about
The camera culling is we will implement camera culling. We're not going to implement this like the culling part of it. This is what OpenGL is handling for us. This is why we went download OpenGL. Okay, so we're almost done. Pixel operation. So this is when we put it up on the screen. So it's going to take each fragment and then determine its contribution to the output result for our image. Okay. There's really nothing more to say about that. This is when it goes up on the screen. So you generate your fragments, determine what the color is going to be for them, and then you actually draw them on the screen. You color your the pixels on the monitor. So what I'll talk about is the difference between fixed function versus programmable layers. So programmable layers in this pipeline allow for shader programming. Okay? I like to think of it as like, man, it's like modding, but with a purpose almost. Like you like if you have a video game, you're like, man, I bet I can make that just look better, but I don't want to write any of the code that is involved in video game programming. I don't want none of that pause menu BS, you know. So shaders are like, you know, modding for your geometry and the stuff that goes up on the screen. So you can do a bunch of really cool effects. So whenever people show me something that's involved with shader programming, it's like, and it looks really, really cool, I almost just kind of go, I'm not like, I mean, I'm impressed that they made that look that way, but that's not like, I know what it takes to make that happen. So it's like, unless they're doing some kind of really complex algorithm, the way that it looks, if it looks cool, is arbitrary to me, man. You know? Because it's just a mod. You dig? If they wrote a program that generated the shader automatically, Zyron was telling me something about some program where they would sample texture information on multiple shaders and then generate a shader just from the way that it looked on a 2D map. That's very impressive, okay? Anyways, the point that I'm trying to make is it's just mods for your rendering. Okay, so this is an example of a shader program. All right, so this is a diffuse shader, and we're going to go over the algorithm involved whenever it comes to the Lambertian model. Okay.
What is float for?
That is just a type. It will return 4 floats, but we're not in that language. I believe that's HLSL.
GLSL?
We're in GLS. Well, I believe we could call it GLSL. I'm actually not like sure what the language is. We just know that it's OpenGL. Okay. Once again, like the reason that it's a big deal is we append our file extensions with like .vert, .frag, and Visual Studio just does not have IntelliSense for that. Okay. And I tried to look for like a linter or something to help us out, but no, we're just straight writing text document code when it comes to the shader programming part, huh?
Can we use VS Code?
Oh yeah, you could, bro. But I mean, it's still just a text editor. You could just write it on your phone at that point, like send yourself a text message. It's just shader. So, right here, so what we say is like one unshaded fragment input record. This is important because you have just no shading on a fragment. Well, you have this code right here, and this code will then translate into the assembly, which does this. And I'm not going to pretend that I understand that right now, okay? But that's literally a translation of the thing that's on the left. It's just in assembly code, all right? I could run down it, but it would take a while. So, obviously, I would do a beam. Dash shader.
I actually have a question about shader.
That shader, though, look at it, bro. It's great.
So it's the same stuff they use in TVs. What was blocking them from black and white till they got color?
Data. More data. So you're looking at the difference in being able to actually have numbers to represent the color spectrum versus a strict. So if you had to say you were only black and white, what would you be limited to as far as a data type?
0 and 1.
Yeah.
Between 0 and
Yeah. So between 0 and 1, because they had some forms, they had like gray and stuff like that. So, so fixed function means no touchy. At least for now, okay. So you can't actually touch any of this, man. Like this. So, what can shaders do for you? So here's a selling point. Man, they can do anything. They can really do anything that you want. So I would say that, so let me just read this real quick. So in short, everything. Obviously needed 2 bullet points for that. And then memegenerator.net. I made that myself. Everything we perceive can be projected onto a 2D plane. And guess what? A 2D plane is assigned the value of monitor. 2D plane is the monitor. All right. So the idea behind it is, how many of you have ever seen the demonstration of, say, like someone going, which one is bigger? Like they give you a thing that's like a bowling ball that's like this big, and then a golf ball that's like that big. And then they go like, which one is bigger? Okay. Yeah, so it's just a matter of like it's a trick of the eye. Okay, you could do anything in a with the way that what angle you're viewing it from.
Distance as well.
Respect.
Well, this is like, yeah. So and then this is like, if it's like the size of a train and it's very far away, it's not going to take up much of your eyeball volume.
Yeah.
Okay. But I mean, if you take a freaking flea and then put it all up in your eye like that, it's going to be huge, right? Okay. So, shaders can basically do, like I said, they can do everything. And whenever we get into cameras and projection, I'm going to show you a lot of demonstrations about how this used to be done. Okay?
Okay.
This used to be done with, I'm not going to say Socrates, but I have some images that are like people, they're sitting and then they're taking, like I have a violin on on a table, and then they're like they open and close this like a panel. Thank you. Small word. So they take a panel and they do like this, and then they punch a hole in it, and then they just keep doing it, like they keep making an outline, and it gives it the perspective view because you're only viewing it from that very specific point of view. All right. So if you know where they're viewing from, you can do a ton of cool things, man. All right, really mess with them, right? Shader viruses and stuff to get people. So there's different types of shaders. Vertex, test question. Vertex, evaluation shaders, geometry shaders, and then this, fragment shaders. All right. I just say this because like that was Bay back then. That was the only kind of shader I knew how to write.
Evaluation.
Mm-hmm.
Like a computation.
Computation.
That's lit.
It's just gonna evaluate 2 things.
I thought only thing a shader could do is just color stuff and make
Yeah, I
it
mean, if
look
you could do all kind of computation on a shader and then like never like put anything on the screen. Like if you all right, here's the thing. If you had some limitation in memory where you could only have a megabyte or so, and then you were really at that limit. Okay.
Yeah.
You had like 1 byte that you could deal with, and you needed to get the function in there. Like I would put it in the shader, and put a comment and go, "Hey man, whenever we like refactor code and stuff, like probably put this in the main program instead." All right, because functions take up memory because they have to execute. So, all right. Okay, so what we'll do is we'll take a break. Yeah? We'll take a break for 5 minutes, and then we'll finish the rest of the slides. We have 4, I want to say 4 slides left.